Hello everyone, welcome to my channel Chemistry by ANR. This is the quick revision of the solutions chapter. We have the formulas of the solution chapter. See the mass percentage if we are finding B is of the solute. So if the mass percentage of the solute we are finding, it is mass of the solute divided by the total mass, that is mass of solute plus solvent, into 100. Next is mole fraction. Mole fraction of the ith component is number of moles of the component divided by total number of moles of all the component. Molarity of the solution. This is equal to number of moles of the solute divided by volume of the solution expressed in liter. So the number of moles is given by mass divided by molar mass, provided the volume of the solution is expressed in liter. Remember that if it is in milliliter, then you are supposed to multiply it by 1000. So number of moles of solute divided by number of the molar mass of the solute into volume of the solution. If in ml, then you have to multiply it by 1000 to make it in liter. Molality is equal to number of moles of the solute divided by mass of the solvent in kg. So here again the number of moles is just replaced by mass divided by molar mass of that solute. If it is in gram, then you have to multiply by 1000 because you have to keep it in kg. Now the relation between molarity of the solution and density. So let us see what it is. Molarity of the solution is equal to mass percent into density into 10 by molecular mass of the solute. Raoult's law for the non-volatile solute. When the solute is non-volatile, vapor pressure is on account of the solvent only. P naught A is the pressure of the pure solvent, vapor pressure. P is the total pressure, and P naught A, total pressure, means of the solution. This is of the solution. And P naught A, again it is the vapor pressure of pure component A, is equal to the mole fraction of the solute, which is B. That is equal to number of moles of solute divided by total number of moles of both the component, because it is a binary solution containing two components only. For a dilute solution, the number of moles of the solvent is considered to be very, very less, and so it is NB by NA, which is the mole fraction. You replace the number of moles by given mass by molar mass and you get this relation. So next, this is how you can find the molecular mass of solute using the relative lowering of vapor pressure. Relative lowering of vapor pressure is P naught A minus P by P naught A. This is the relative lowering of vapor pressure. If it is lowering of vapor pressure, only lowering of vapor pressure, then it will be P naught A minus P. This is the lowering of vapor pressure, not the relative lowering. For relative lowering, it is with respect to P naught A, so divided by P naught A. Next is Raoult's law for volatile solute. For the volatile solute, first you have taken non-volatile. Now volatile, if I say, that means the vapor pressure is on account of both the components A and B. So that is equal to PA is equal to PA naught into XA, PB is equal to P naught B into XB, and the total vapor pressure is on account of both the components, and you replace it and get this relation. Next is the next colligative property, elevation in boiling point. So your delta TB is the elevation in boiling point, which is equal to Kb into the molality. M is molality of the solution. It is molality of the solution. So this is it. So this is equal to Kb into, you replace the molality by number of moles of solute. So WB by MB, mass of solute by molar mass of solute, divided by what? The mass of the solvent, WA, in kg. So this is given in gram. So you multiply it by 1000. So from here you can find the molecular mass of the component B using the colligative property which is elevation in boiling point, delta TB. Now delta TB is TB minus T naught B. T naught B is of the pure solvent or pure component. Now TB is of the solution. Now depression in freezing point, that is again delta TF is equal to KF into M. M is again the molality of the solution, and this is how you put the values and get the value of MB with respect to delta TF. Osmotic pressure, now here always remember that it was elevation in boiling point, and so delta TB was TB minus TB naught, but delta TF will be depression, so TF naught minus TF. This is the depression in freezing point. Now osmotic pressure is pi. Pi is equal to CRT, where C is the molar concentration. So C is the molarity of the solution, and so this is more convenient to perform. So NB by V, that means number of moles of solute by volume of the solution in liter. You replace the number of moles by mass divided by molar mass and get this relation for calculating molar mass of solute, especially the molar mass of macromolecules, because here this osmotic pressure method, here you can carry out at room temperature. You can use molarity, which is more convenient, and you get a measurable value of the colligative property with respect in comparison to other colligative properties. Now relation between osmotic pressure pi and the density of the solution, this is the relation. Pi is equal to the relative lowering of the vapor pressure, this into D into RT by MB. So this is the final relation again with pi and delta TF if it is asked. So this is the relation. This is one colligative property to the other. So osmotic pressure to relative lowering of vapor pressure, osmotic pressure to depression in the freezing point. This is the relation. Now, if there is association and dissociation taking place, then we have a factor which is known as Van 't Hoff factor, and using this Van 't Hoff factor, the colligative properties are getting modified. So this modification of the colligative properties are just you multiply it by the Van 't Hoff factor I, and you should remember that I is equal to the normal molar mass divided by the observed molar mass or molecular mass. So this is divided by the observed molecular mass, or you can say which is equal to the observed colligative property divided by the calculated colligative property, that is I. Or you can also say I is equal to the number of moles of particles, after association or dissociation, divided by number of moles of the particles before association or dissociation. So if association takes place, if there is association, then always remember that I is less than 1. And if there is dissociation, then I is greater than 1. And when there is no association or dissociation, I is equal to 1. So that was the Van 't Hoff factor. So this is the revision part of the Van 't Hoff factor. And you see in all of the colligative properties, this Van 't Hoff factor is introduced. Now, if alpha is the degree of dissociation, then alpha is equal to I minus 1 by N minus 1. What is N? The number of ions produced per formula of the compound on account of this dissociation. And for association, alpha is equal to the degree of association, which is equal to I minus 1 by N minus 1, or you can just reverse it and write, because 1 by N is less than 1. Now, this is again a question which is asked in one of the board exam, relation between the molar elevation constant and enthalpy of vaporization or fusion. So this is the relation with respect to delta H vaporization and with respect to delta H fusion. Now, values of R in all the possible unit, because in numericals you need this. Remember that these two values of R are most widely used. 0.0821 liter atmosphere per Kelvin per mole or 8.314 joule per Kelvin per mole. These are the other units of R. These are all the values and the units of R. So this covers up almost the most important part of the solution chapter in order to help you in solving the numericals. So bye all of you. See you in the next video.